We're going to review some important properties of greatest common divisor in section 5.5, and then we're going to move right into section 5.6, which is the fundamental theorem of arithmetic. We're going to skip a lot of parts of these two sections, and there's only a few problems that I'm going to want you to be able to do. Let's remind ourselves of some facts that we learned about when we played with the Euclidean algorithm and reversing the Euclidean algorithm to get those Bézout coefficients. So here's a theorem. If you have D, which is the GCD of two positive integers a and b, then the set of linear combinations of a and b, set of integer linear combinations of a and b, is equal to the set of multiples of D. Now, this is a really nice example of a proof of equality of two sets where you show that one is a subset of the other and vice versa. The other is a subset of the one. So just to make this proof a little easier to follow, we're going to give each of these sets a name. This first set we're going to call S, and the second set we're going to call T. The strategy is going to be to show S equals T by proving S is a subset of T and T is a subset of S. If nothing else, it's a good idea to think of this next part as a good example of showing that two sets are equal to each other using the one is a subset of the other and vice versa method. So let's start by showing that S is a subset of T. The strategy to do that is to start with an arbitrary element in the first set. So we'll let X be in S, and then we know we need to show that X is in T as well. So if X is in S, that means we can write X as a linear combination of A and B for some integers S and T. We also know that D divides A and D divides B, where D is the GCD of A and B, which means we can rewrite A and B as these here. A is some multiple of D, B is some other multiple of D. The A prime and the B prime, again, that's just, we don't have enough letters, it's not a derivative, this isn't calculus, it's just another name for another letter. X equals AS plus BT, which when we substitute information from these two equations gives us dA prime S plus dB prime T. We can factor out D, and we know that what's left in the parentheses is an integer. That tells us X is a multiple of D, which is what we wanted to show. In order to show X is an element of T, you have to show that X is a multiple of D, since that's what that set means. Now we need to show the other direction. Part 2 is saying T is a subset of S. That's what we're trying to prove. Okay, so we're going to reduce this to a simpler task, which is to show that the greatest common divisor, D, is an element of S. We know that in particular, D has to be an element of T. And if we show that D is also an element of S, then we can actually multiply D by whatever we want, and then we'll show that that multiple will also be an element of S. So let's see how that works. So let's consider the positive elements in the set S. Remember, S is the set of linear combinations of A and B. So let's just consider the positive linear combinations, the linear combinations that end up being a positive number. One element in there is A, because we can write A as A times 1 plus B times 0. So A is in S plus. That tells us that S plus has something in it. And we're going to use a fact that we skipped from a long time ago called the principle of well ordering, which basically says that any set of positive integers has to have a smallest element, a least element. Okay, so let's say this set of positive elements of S has a smallest element, and we'll call it E. That means E can be written as a linear combination of A and B. Again, this S star and T star is just, we don't have enough letters, so we're using stars to differentiate them from other uses of S and T. So we know that A is an element of S plus, which means E has to be less than or equal to A, which means we can apply the division algorithm to A and E, and we conclude that if the remainder here is not 0, if the remainder is positive, then we can write R as A minus EQ and replace E with this linear combination here. Do a little bit of algebra, and we've shown that R is now a linear combination, an integer linear combination of A and B. But E is the smallest element in S plus, so we can't have that R is positive and less than E. So that means R has to equal 0, which tells us that E divides A. Using this linear combination for B shows that B is an element of S plus, and we can use the same argument to show that E divides B. That says that E is a common divisor of A and B. So if F is any, now we're going to just kind of generalize this observation. If F is any common divisor of A and B, that means F divides A, F divides B. It means F divides any linear combination of A and B. In particular, F is going to divide E, which means F is less than or equal to E. So what we just said is if you pick an arbitrary common divisor of A and B, then F will be less than or equal to E. That means E is in fact the greatest common divisor. That means E is actually D. So we're done. Again, the most important fact here is to associate the greatest common divisor of two integers with some linear combination of those two integers. This is what we did with the Euclidean algorithm and reversing the Euclidean algorithm to get those Bezout coefficients. So GCD of A and B is the smallest positive element in the set of linear combinations of A and B. And if you have any two non-zero integers A and B, you can find S and T such that GCD of A and B is equal to that linear combination, AS plus BT. So this isn't really too new because we already played with this with actual numbers. But the important thing to keep in mind is that the GCD of two non-zero integers is going to be some linear combination of those two integers. And in particular, A and B are going to be relatively prime, which is the same as saying that their GCD is 1, if and only if you have a linear combination of A and B that gives you 1. We're going to use this a lot pretty soon, so it's important to think of that particular example. Speaking of examples, let's talk through a couple of examples here. So 5 and 7 are relatively prime. They're both actually prime, so they're definitely relatively prime to each other. 14 and 27 are also relatively prime. They have no common factors other than 1. So that means their greatest common divisor is 1. Finding the linear combination of each of these pairs of numbers to get 1, you can either use the Euclidean algorithm like we have done, or you can just kind of guess and check. Playing around with 5 and 7, you can guess and check that 3 times 5 minus 2 times 7 will give you 1. Similarly with 14 and 27, you don't have to use the Euclidean algorithm. You can just play around with numbers and you get that 2 times 14 minus 1 times 27 is equal to 1. So for something like this, for two numbers that are larger, it might be harder to just do this by inspection to find the S and T that gives you the linear combination that equals 1. So you would probably want to use the extended Euclidean algorithm for it. So go ahead and give that a try. Similar question with some larger numbers. Again, it's fun to play around and try to do it by inspection. If the numbers get bigger, it's a little harder. And then finally, this is a cool little fact. Because I can write n and n plus 1 as a linear combination equaling 1 using the cleverly chosen coefficients -1 and 1, I have now shown that the GCD of n and n plus 1 is equal to 1. So in other words, any pair of consecutive positive integers is going to be relatively prime. Euclid's lemma is a fact that we'll probably end up using later. It says that if you have three integers, a, b, and c, if a and c are relatively prime, and c divides the product of a and b, then that means c must divide b. So let's talk about a thought process for how we would prove something like this. Given that the GCD of a and c is 1, we can assume that as plus ct is equal to 1 for some integers s and t. And given that c divides ab, we could write ab as cx for some integer x. And the conclusion we want is to show that b is equal to cq for some integer q. Remember, WTS stands for want to show. Okay, so we need some information about b. And we have these two equations that are given. Notice that b is equal to b times 1, which means we can multiply both sides of this equation, where 1 is by itself on one side, by b. This is not okay here, the way that it's written. We don't multiply an equation by a number, we multiply both sides of an equation by a number. So that's what's going on here. We get ASB plus CTB. So now to show that C divides a sum of two numbers, we need to show that C divides each term. That's a fact from a theorem in an earlier section of this chapter. So CTB, it has C as a factor right there in front of us. So we know C divides CTB, and ASB can be written as AB times S. We're given that C divides AB, which means AB is a multiple of C, so we're done. So here's what we just discussed in a more organized format. This is the actual proof, what it would look like. So take a moment to study it. See how the different parts of our discussion are included in this proof. Okay. A couple of quick corollaries. If you have two integers, a and b, and p is a prime that divides a times b, that means p has to divide a or b. It's important that p is prime. I'm going to jump to this situation here. If p were composite, this fact would not be true. So think about this. 6 divides 60, which is 4 times 15, but 6 doesn't divide 4 and 6 doesn't divide 15. But if we had a prime, if this were a prime number instead, where it divided the product of two integers, we know that that prime has to divide one or the other, or possibly both. So for example, 5 divides 15 times 25, and 5 is prime, so this corollary guarantees that 5 divides 15 or divides 25. But in this particular case, both are true. Remember, this is an inclusive OR, so it's X or Y or possibly both. Building on that, we can kind of generalize this idea. If we have n integers, and p is a prime that divides the product of all of them, that means p must divide one of those factors, one of those integers. Okay, so that's it for the 5.5 portion of this section. Just to sum up, we're talking about linear combinations of two integers that give the greatest common divisor. And then we had a couple of helpful facts. I only want you to do one problem from this section, and I want you to do it using just plain old Euclidean algorithm. So think about how you might do that for this one. Or you could do it by inspection, maybe, possibly. Either way would be good. But yeah, that's a practice for you.